Welcome back to Breakdown of Science. Today is our first official episode.
Yep, which is awesome.
We're finally getting to it.
Yeah.
Today it's me, Jan.
And it's me, Michelle.
Yeah, we will be your hosts for today's episode.
Mm-hmm.
This week we're covering a recent science article that has been presented in multiple news sources.
3 weeks ago, right? It was published 3 weeks ago.
Yeah, about 3 weeks ago on the 17th of April was when it published. And we found it a bit interesting.
Yeah,
so
because it's like about life on a distant planet.
Potential life.
Yes, obviously.
So we looked through a few of the major news articles. The links of the few that we looked into will be in the description.
Yeah. And if you're interested, you can just go to the links and
read them as well.
Yeah.
We will also be adding the link to the study article, the actual science article, if you're interested in a more detailed and more scientific explanation of what's going on. So from what we've seen of these news articles is that majority of them do end up covering
most of the results.
Yeah, most of the results, the key results.
Yeah.
And interpreting the meanings as well. And one thing that was interesting is how they not address, but they continuously brought in experts for talking about both sides.
Yeah.
And what was nice to see was that when the researchers of the article were brought to interview, they continuously said that while their findings were significant, it's not yet, it cannot be 100% proof that life does exist in this planet. And so that's something to keep in mind. While the study gives evidence that life is existing.
But you have to be cautious.
You have to be cautious, yes. We cannot say it for certain. So what is this study looking at that is giving them the certainty that life does exist on this planet, K218b?
So I think it says that there are, for example, dimethyl sulfide and dimethyl disulfide, which are basically you can see dimethyl sulfide as a molecule, no, an atom, right?
Dimethyl sulfide is a molecule.
Yeah, exactly. Yeah, so you can see this as a molecule which has one sulfur atom, while dimethyl disulfide has 2.
Yep. Basically, this is just a molecule, a methyl molecule with a sulfide attached for simplicity.
Exactly.
And
both of them symbols smell like rotten eggs, but dimethyl disulfide smells more stronger and definitely more pungent because of the extra sulfur.
Yes, exactly. And both are produced by organisms like animals, plants, or bacteria, and it's mainly, and majority of it is produced here on Earth by marine life, like phytoplankton.
So what is it? So it's basically a microscopic, which is capable of photosynthesis, found in oceans, seas, and fresh water.
Yeah, just plankton.
Just a plant.
Yeah, that's plankton that uses light as food.
Exactly, basically. And they're also aquatic food for majority of the creatures. Yeah.
So to be able to observe these elements in the atmosphere of K218b, or we'll just shorten it to K2 for simplicity, they used the James Webb Telescope, the most recent major satellite launch of a satellite from NASA.
Yeah, it was launched in December 25th in 2021.
Yep. And its main job is to conduct, it's designed to conduct infrared astronomy. And it's currently placed in a solar orbit near what's called the Sun-Earth L2 Lagrange point.
Yeah.
And
Can you explain it?
Yeah. So a Lagrange point is a spot in space where the gravity of two large bodies balances out, and letting a smaller object to stay in a fixed position relative to them.
Okay.
meaning it follows both the Earth and Sun's movement in sync. And L2 is a specific point in that region, point in space where the Sun, Earth, and the object, in this case the James Webb Telescope, line up in that order. So it's the Sun, Earth, and then the James Webb Telescope.
Okay.
And in this study, the equipment that they mainly used was the mid-infrared instrument low resolution spectroscopy, or the MIRI LRS.
So MIRI provides like imaging and spectroscopy observing modes, which is like from 5 to 28 micrometer wavelengths. So like what's a micrometer? Well, like an example, like a typical human hair is like about 100 micrometers. So you can see a micrometer about like 100 times smaller than a human hair. So that would be a visual explanation of it. Yeah.
And infrared, for basic understanding, is just an outside our normal range of visible light, but just beyond the red end of that spectrum.
Yeah.
And since we're also talking about light, this is what spectroscopy mainly works on. So light has multiple wavelengths. That's how we can see multiple colors of light.
Yeah.
And when it hits something, it separates into all those wavelengths, hence giving us those colors. And an interesting aspect of like elements and just everything is that each of them have almost a unique wavelength to them. So like almost every element in the periodic table has a unique set of wavelengths because of how the light separates when it gets hit.
Yeah.
And a spectroscope, so the machine, collects the light that is separated from the object that was hit and then records those wavelengths. This information then later on gets compared to a database of
the other elements,
other objects, other materials that have been like already studied, and compared to like understand if this is actually what's being observed and stuff. And in this case, the low level refers to the region of wavelength that the device is recording, which is like the spectroscope itself is 5 to 14 micrometers.
So it means it's in the infrared. So the planet itself, it's called K2-18b, but we're calling this K2 for
simplicity reasons.
Yeah, exactly. So it's a Haitian planet, which I will talk about later, in the habitable zone of a red dwarf sun, about 124 light years away from Earth. So what's a habitable zone? So it's basically...
I can answer that.
I can answer. Yeah.
So the habitable zone is like a section of space around a sun where liquid water can exist. When water can exist in its liquid form on the surface of a planet.
So basically like Earth.
Basically Earth is like the main aspect of it. We compare majority of habitable zones to Earth's because that's the only model that we
have.
Like definite proof that life exists.
And for red dwarf sun, you can see it as like a sun, just smaller, older, and dimmer. But it's also cooler than our sun, and because of that, it looks red instead of like yellow and orange.
And as was said, like this planet is 124 light years away from Earth. And to get an understanding is that light year isn't a measure of distance per se. It's more of a measurement of time that it takes the light to reach the destination within a year. And the reason we usually use light years instead of kilometers or like miles when talking about more or less talking about deep space is because of how vast, how empty space is, that it just talking with kilometers miles would give us like huge numbers that are just like cumbersome to like properly evaluate basically. And so you said earlier that this is a Haitian planet.
So it's basically a oh my god how do you pronounce this?
Hippopotamus.
Yeah, I suppose.
No, hypothetical.
Yeah, exactly. Hypothetical type of a planet that features, as you mentioned before, a liquid water ocean underneath a hydrogen-rich atmosphere.
So it's not like it's not an Earth-like planet.
No, it's yeah, hydrogen-rich.
Hydrogen-rich. Yeah.
Yeah, it's definitely not like Earth. So like in the study, it says like it's 2.6 times the radius of the Earth.
Mhm.
So that
Could you give us a bit of
yeah. Yeah.
like perspective, a bit of perspective of like how big that 2.6 times actually is?
Yeah, sure. So like the radius, like the Earth equatorial radius, it's like around 6,378 kilometers, and that's basically like a trip from Germany, like from Düsseldorf to New York, which is about 6,300 kilometers. So it's about like 78 kilometers short.
Mm-hmm.
And so at 2.6 times, it's basically 16,582.8 kilometers. So it's a lot.
Yes,
It's very
definitely.
Yeah, definitely. So it's basically, so in this case, it's from Düsseldorf to Sydney, which is about 16,500 kilometers.
And you said that it's a hydrogen-rich atmosphere. How does that compare to Earth's atmosphere?
So in Earth, I think it's about wait, how many zeros is that? Oh, 4. Okay.
4.
0.00055% of our atmosphere, and in this planet, it's like around 80 to 90% of their atmosphere. So which is
massively differently.
Yeah,
There's a huge like gap
difference.
between
Which is insane.
And interesting enough that besides from what I remember, a majority of the articles that we read didn't give clear explanation to like how big 2.6 times was. They would just give the number. They would also give the number of the mass, which some say like 8.6 times as massive in terms of mass.
Yeah. Or they just say that it's like 2.5 times Earth.
Yeah, they didn't. Interesting enough, they didn't really talk about. They didn't mention if it was in terms of the radius, or in terms of the diameter. If it's some did say in terms of mass, but when it came to the 2.6 value, they would just say it's 2.6 times as large. They didn't really. These news articles didn't specify if it is the radius or in diameter or maybe I don't know circumference.
Yeah, but can you tell me like about the results of the study?
Yeah, so we wanted to know how accurate what these news articles have found is. So we went into looking into the actual study itself and trying to break down what the results are. Yes, indeed. So the spectrum shows that it's multiple spectral features between 6 to 11 micrometers. That the study says are best explained by a combination of both DMDS and DMS. So by spectral features, they're referring to like specific points or peaks or even like lines on a spectrum that provides information about the substance being studied. And
should we talk about what the spectrum is, or is it like given?
It's
given.
It's understandable what spectrum is. We don't really have to go into that detailed. So the study does say that it is a promising biosignature in habitable for a habitable exoplanet. And they came in terms of how significant these values that they found were. They are saying that it showed a significance of 2.9 to 3.2 sigma significance in sigma in terms of like standard deviation, which is a statistics things.
By the way, just like
yes.
So a biosignature is basically, you can see it as a scientific evidence of a past or present life on a planet. So that's what it means.
Thank you for the clarification. Now going back to the significance. So what a sigma significance tells us is how likely it is that a signal or an information that was received is an actual thing, it's real, it's a factual thing.
Yeah, yeah.
Or if it's just random noise, just by chance.
Yeah.
And so what the numbers specifically mean. So at 2.9 means that there's about 0.19% chance that the results are just due to random events, random events. That isn't because there's DMS, but it just could be a fault with like the machine or something like this.
But
errors in calculation, something.
But the results are like 99.81% correct, right?
It's not 99% correct. What it's like referring to with like a 99.81% confidence is that how sure we are that the result is real. We believe that it's actually because of the DMS and DMDS rather than just random events.
Oh, okay. So what's the difference from what I said?
You said that it's like the actual thing.
The actual, okay.
It's still not an actual thing. This is like a possibility.
Okay.
There's like the possibility is a 99.81% possibility that the results are correct.
Right.
It's still not confirmed.
It's not factual.
It's factual to a certain to this fact. That's what like it actually means.
Okay.
So, and so it's saying that it's 2.9 to a 3.2. A 3.2 sigma significance means that there's a 0.07% chance that the result is just noise, so 99.93%, which is better. However, this is still not it's enough to make speculations and see that there is potential for this endeavor and for future research, but it's not like enough to say that this is a definite finding.
But it's like 99.93%. It's just short of 0.07%.
Yes, but in science we want to be as accurate as we can before we make something, before we jump the gun and say that aliens are real and have the whole world go crazy.
Yeah, sure.
Though back when like the pandemic was going on, the US government did come out and say, hey, aliens are real, and no one really gave
a shit.
You gave a damn about.
Okay, sorry, it's PG 13 family?
I guess so. We're just talking here, it doesn't really matter much.
Yeah.
But yeah, and when they did it, no one really cared.
Yeah.
So who knows? Maybe they will care about this one when it comes. But yeah, so the in most science they require a 5 sigma significance, which means a 99.99994% confidence.
Wow.
You need to be super specific. Like this means that like a 5 sigma means that there's just a 0.00006% chance that it's like just a random thing happening.
Yeah, I think you should like talk about like what sigma is. Maybe.
I mean, we mentioned before that it's like it's just the sigma is like referring to the standard deviation in statistics when you're looking at like the normal distribution of data. Of like the spread of data, and so the more standard deviation that is being mentioned, that's more of the data being considered, from my understanding of it. And so
I think at 3 sigma it's like what
a more like that's a 3 sigma. It's roughly like 99.7 if I remember correctly.
And with 5 sigma it's.
At 5 sigma, it's 99.999994%. So, in our sense, it's like it seems like a small gap between the two.
Yeah.
Like the one has a 0.7, the other has a 0.0006% chance of like error.
Yeah, true. Yeah.
So like, every time, like at any moment when someone says like a 0 point something,
Yeah.
0.7, even if it's 0.1% or 0.9, we assume it's like a very little chance or something like this.
Yeah.
But even though it's like little, for it to be like a proper factual thing that we can point and say that indeed is that, it has to be even a lower percentage of error because we want to be as sure as we can.
Yeah, but there's never a guarantee that you will get 100%.
I mean, no. I mean, statistically, you wouldn't always get 100,
exactly.
but I would say it's the role in science to try and get as close as we can to 100% the truth of the situation.
Yeah.
But yeah, that's about it. Yeah. So going back to our study, so
we were at the high sigma.
Yes. So these levels, so like a 2.9 to a 3.2 sigma significance, these levels do suggest a tentative but not a definite detection. So, as we said, it's statistically strong evidence, but it's not conclusive that there is actual life. It's just saying that there's a possibility of it. And when we were like reading through some of the articles that we saw and the quotes from the research team, most of them did say, especially with the main author and the co-authors, they did mention that there's a chance that they could have missed something or that the data is not entirely accurate. So they want to continue. So they're still actually continuing observations. So far, we didn't really see anything new come out in terms of like an update on this. So the research could still be ongoing. But so far, everything seems quite interesting, and it's quite a strong lead for future research.
Definitely.
Yeah. And now we have that. And now going into what the actual values are. So the researchers said that this is a quote from the article. It's in the research article. It's saying that our present MIRI abundance estimates of DMS and or DMDS at mixing ratios of about 10 to the power -5 to 10 to the power -3 could therefore imply strong biological activity on the planet in comparison to Earth.
Yeah, the mixing ratio is just like how much of a gas is like in the air. So in K2, it's basically like, for example, for DMS or DMDS, it might be around 10 to the, as you said, 10 to the power of -5 to 10 to the power of -3.
But on Earth, DMS is usually around 10 to the power -9 or lower in the air. They in the actual some of the news, they did say that there could be
increase.
This is not an increase, but they're saying that this 10 to the power -9 is the global average. But there can be pockets, especially in marine ecosystems, there are pockets where this concentration can be higher because of the local biological activity of that space.
That's interesting.
Yeah, and so with these values, we can see that the K2 18b like may have 1,000 to 1,000,000 times more DMS-like gases than Earth.
Wow.
And for a bit of like context on like what these values actually represent, a mixing ratio of 10 to the power -3 only accounts for like 0.1% of the atmosphere, which is in parts per million. That's about 1,000 parts per million. While a mixing ratio of 10 to the power of -6 is like 0.0001% of the atmosphere, which is just 1 parts per million.
Parts?
Yeah, 1 part per million. Parts per million. Yeah. And they did look to see if there is a possibility that these like DMS can be created through an abiotic factor or abiotically. But they did look at other researchers who have done experiments with like methane and CO2 to see if breaking them down through UV and other like radiation could result in DMS production.
You mentioned like about abiotic factor. Can you explain like what it is?
Yeah, so an abiotic factor is a non-living part of an ecosystem that shapes that environment.
Okay.
So abiotically refers to something being done without life.
Okay.
As I just said in the experiment that the study was like referencing, they used UV radiation and some other types of radiation to hit like methane and CO2 molecules to see if that ends up forming DMS or DMDS.
Okay.
But from what they saw, the resulting atmospheric levels when doing this experiment are like far too low to explain the observation at this exoplanet.
Okay.
Without incorporating like a biological source for the development of these gases.
Yeah. So if there's abiotic, then what's the biotic factor?
Biotic factor, as like we also like mentioned here on Earth, it's like mainly marine life for DMS and like phytoplankton and stuff. So there could be like organisms like something like plankton or something on the ocean planet. Hycean planet, that could be the source of these gases being formed.
So could we see that, for example, abiotic factors, it could be seen as like chemical compounds?
Abiotic factors just refer to anything that's not a
living
reaction. Like random chemical reactions are abiotic. Reactions with like radiation are abiotic. Random events that don't have biological components in them are not like helped by a biological aspect is abiotic in this context. Another thing that experiment that was being referenced as I said, the experiment referenced in the study involves a laboratory simulation where scientists tried to mimic possible atmospheric condition with like gases like methane and hydrogen sulfide. And then, as I said, expose them to UV light or even like electrical discharge to see what molecules are produced abiotically. But the concentrations produced are extremely low and short-lived and nowhere near the high levels that are being like suggested are evident in K2-18b's atmosphere.
Okay, so what does that mean exactly?
It means that this is a way to like check if maybe K2-18b like levels are being formed through an abiotic factor. If it's being formed by an abiotic factor, it means that the likelihood that it's because of a living organism is lower. But seeing as the like hypothesized concentrations aren't matching up with laboratory experiments, it's more evidence towards the fact that there is not that there is, but there might possibly be a biological component to the development of these gases.
So there could be life on that planet?
Could be, and a strong could be. Because again, it's not fully certain, but it's statistically strong, as was stated.
And the amount of times we said it could be, but it's.
I mean, we aren't the only ones. The articles that we read, almost every other sentence ended with saying
it could be.
It could be. It might be. Potentially. Perhaps. Mayhaps.
At this point, I think it's hilarious.
It is a bit
redundant.
It's redundant, but sometimes you have to repeat it constantly.
That people doesn't take like parts of it and just make a mayhem.
It doesn't take doesn't misunderstanding or anything. It just runs with it or something. It can be redundant. Yes. But I do find this quite cool.
Yeah.
Another thing is that the same scientists who are actually working on this, who work on this,
Yeah.
are also the same ones who have like hypothesized the existence of these Haitian
Really?
worlds. Yeah. They did this, and it was back in 2023, I think, was it?
Yeah.
And back in 2023.
I think it's about the methane and carbon based.
So
in the plan.
In 2023, the researchers did say they found evidence of methane, carbon dioxide in K218b's atmosphere, and in some other news they mentioned that their previous studies, when they did this, also revealed potential existence of DMS, but those instruments were not. It wasn't that it's purpose-built, but they weren't accurate enough to be able to determine if what they are sensing is actually DMS. But in this study, they used the James Webb Telescope again and used different instruments on it to more accurately understand if what they discovered, not discovered, but what they saw last time is actually DMS.
When you say different equipment, do you mean like the MIRI LRS?
Yeah, the MIRI LRS. I don't know what exactly they used last time. It wasn't mentioned in the news articles, and I probably should look at it a bit more.
Yeah.
But that's what they did. Yeah. And when it was in 2021 when this group of researchers also hypothesized the existence of these Haitian world's existence.
Yeah.
It's still like a hypothetical world. It's because in astrophysics and astronomy and stuff, things are so far away that you only have fragments of information to pull out. So
I think it's still impressive that they were able to get this much information.
But there are some of their colleagues that were interviewed in the news article saying that the likelihood that this planet is a Haitian, one of them said the likelihood that this, I'm paraphrasing here, but the likelihood that this planet is a Haitian world is the same as also being a magma world, meaning a world that's just lava. So there are quite a lot of skepticisms in terms of the significance of this evidence.
More into that, I also heard something about the K218b being a mini Neptune.
A mini Neptune or a sub-Neptune. Yeah. It's just a way of classifying the size of the planets.
Okay.
So it's basically.
But it's not like a Neptune, is it?
It doesn't mean that it has characteristics to Neptune. Yeah. It doesn't necessarily mean that it's a gas giant. Specifically, Neptune is a icy gas giant. Yeah. And calling someone a mini Neptune or a sub-Neptune doesn't refer to its characteristics as a planet, but it's referring to it in terms of size. Yeah. So it basically means that it's bigger than Earth, but smaller than Neptune. I did look and see that when being referred to a sub-Neptunian, a Neptune planet, Neptune as a planet, has 4 times the radius of Earth.
So it's huge.
Yeah, it's huge, yes. So basically, what we had what we set for K2's radius of being 2 times 6, basically that's twice, which is almost a round trip from Düsseldorf to Sydney, and maybe halfway back, maybe as well.
Yeah. So the hypothesis, K2 being a mini gas giant with no surface, I guess that's wrong. Or would you say it's not wrong?
I think. I can't really say if it's wrong or not.
Yeah, true. We're not that
knowledgeable about it.
But it's not a gas giant, is it?
It could be. Because one of their colleagues said that it's as likely as to be a magma world. So there's a chance that it could be a gas giant, mini gas giant, because there's like evidence that, for example, Jupiter. I don't know if this is also for like Saturn's situation as well, but for Jupiter there is some evidence saying that it's just a very thick atmospheric planet with and it does have a surface which is a hydrogen ocean, I think it was called, or something like this. Let me look it up. Jupiter.
Jupiter having an ocean.
If I can, so say here it's like from NASA. The composition of Jupiter is similar to that of the Sun, mostly hydrogen and helium. Deep in the atmosphere, pressure and temperature increase, compressing the hydrogen gas into a liquid. This gives Jupiter the largest ocean in the solar system, an ocean made of hydrogen instead of water.
I didn't know that Jupiter had a composition similar to the Sun.
There's for quite a while, people have called Jupiter a failed star because they're.
But isn't it a planet?
It is a planet. The way that stars were formed is just a massive concentration of hydrogen and helium.
Yeah.
Just continuously like gathering and pressurizing from gravity to the point where it just ends up creating nuclear fusion.
Wow.
And then you have a sun.
Okay.
Nuclear fusion is when you merge two atoms. Nuclear fission is when you separate. That's how nuclear power is made. Yeah. But nuclear fission, which is also being researched, and we can go on that maybe another episode. Yeah. We'll see. But quickly to finish this tangent a bit. Yeah. The reason they're calling Jupiter, they did call Jupiter a failed star, was that because of its concentration of hydrogen and helium, having so much. Yeah. And because it's if I remember my astronomy correctly, it was the first planet that was formed in the solar system. Yeah. And it was, so it was the sun and then it was Jupiter with a bunch of rock and gases in the atmosphere. So there's still a lot of material it could gather up. Well, because of events, it didn't. And because it didn't form a star, like a dwarf star or whatever, they are calling it a failed one. But if you actually look into the values, Jupiter is still quite small compared to the Sun. Yeah. And you still need a bunch more helium and hydrogen to even start up. Okay. Because there was some discussion saying let's just if you shoot a laser to Jupiter, it'll just ignite it into a star. But it won't. There is not enough hydrogen and helium to support that.
Do you think it would still absorb hydrogen and helium? Do you think there would be a possibility?
I mean, it can absorb if it gets to a source close enough. If there's enough, the reason it will absorb is because there's gravity. Yeah. Anything that falls within the gravity well of Jupiter will be absorbed by Jupiter. That's how meteors and comets hit. Well, not comets, but meteors hit and all that. Yeah. Yeah. Anyway, do you have any questions that you wanted to explore?
Honestly, you already answered most of it.
Yeah. But yeah, I do find this quite interesting, and I hope you viewers also found this interesting.
If you guys have any questions, just
feel free to reach out, comment, and ask us. Thank you.
You can also DM us in Instagram.
Yeah. Thank you so much for listening to our first official episode. I hope you enjoyed listening.
Yeah, I hope you enjoyed Jan's research on this.
And I hope you researched Michelle's questions and discussions as well. Yeah. It was fun doing this.
Yeah, definitely.
Definitely. And hopefully we can do many more to come.
Yeah. I think next time we're going to do a debate.
Next week we're going to, not a debate, but we're going to look into either debates or discussions, seeing what comes up. Yeah. Or we will let you know what the topic is going to be when it comes out.
Yeah.
So stay tuned for that episode.
Yeah.
And again, thank you for listening.
Yeah. Thank you so
Have a
much.
wonderful rest of your day.
Yeah.
And goodbye.
Goodbye.